Have you ever pondered why carbon, an element with just 6 electrons, forms the backbone of countless complex organic molecules? The answer lies in a fascinating concept called hybridization. Hybridization is the intermixing of orbitals of slightly different energies to produce new orbitals of equivalent energy. In essence, it's like taking a few solo musicians, each with their unique sound, and forming a harmonious band where every member contributes equally to the melody. Let's delve into this concept step by step. Firstly, consider the carbon atom, the star of organic chemistry. With 6 electrons, 2 in the inner shell and 4 in the outer, carbon is ready to form bonds. But here's where it gets interesting. These 4 outer electrons reside in different orbitals, 2 in the 2s orbital and 2 in the separate 2p orbitals. If carbon were to form bonds using these orbitals as they are, the bonds wouldn't be equivalent. But nature loves symmetry and stability. So, what does carbon do? It shuffles its electrons around in a process we call excitation, moving one of its 2 s electrons into the empty 2p orbital. Now, carbon has 4 unpaired electrons, each in separate orbitals. But these orbitals are not of the same energy. To rectify this, carbon employs hybridization. The 2s orbital and the 3 2p orbitals merge to form 4 new hybrid orbitals, all of equal energy. These are called sep3 hybrid orbitals. And voila! Carbon is now ready to form 4 equivalent bonds with other atoms, creating a symmetrical tetrahedral structure, which is the basic building block of many organic molecules. But hybridization is not a one-size-fits-all concept. Depending on the molecule's requirements, carbon can form 2 other types of hybrid orbitals, sp2 and sp. In sep2 hybridization, 1s and 2p orbitals intermix, leaving 1p orbital unhybridized. This results in a trigonal planar structure like in ethene. In sp hybridization, 1s and 1p orbital combine, leaving 2p orbitals unhybridized. This gives a linear structure such as in ethine. So, in summarizing, hybridization is the secret behind the versatility of carbon. It is the process by which carbon can form equivalent bonds, creating stable, symmetrical structures. Whether it's SE3, sp2 or sp hybridization, each type lends a unique shape and property to the molecule, making organic chemistry the diverse and complex field that it is. Remember, understanding hybridization doesn't just help us predict the shape of molecules, it also helps us understand their properties, reactivity, and ultimately, their role in the grand scheme of life. So the next time you see an organic molecule, you'll know there's a harmonious band of hybrid orbitals playing the symphony of life.